Welcome to this lecture series on building a variational Monte Carlo program and Physics 4411. The overview of this week is to look at some of the essential ingredients which are needed in order to build a variational Monte Carlo program. And one of these essential ingredients is an algorithm, a famous one, which is called the Metropolis algorithm. We are going also to look at statistics and the theory of Markov chains, and we are going to discuss a little bit on how to structure the code. The videos will be uploaded after these lectures. And last week, we discussed some of the basic ingredients which are needed if we want to establish a variational Monte Carlo program. In setting up a C++ or Python code, which we will practice during the lab sessions, we have an excellent framework which was developed by a former student, Morten Ledum. And this framework is something you can reach at this GitHub address. And this is something which we discussed also last week during the lab sessions. So you should feel free to opt for the programming language you feel most comfortable with. In the lectures, we are going to use Python because we can often run and visualize demonstrations immediately of specific algorithms and parts of the program, which we are going to keep adding. And then in the lab sessions, Øyvind will also talk about the C++ implementations. And you should feel free to use these programming languages, or as we discussed last time, if you're more familiar with Fortran, feel free to use Fortran. If you're more familiar with, let's say, Julia or Rust or all of these languages, feel free to do so. So these notebooks, which you will see now, which are the lectures which define the lecture material for this week, have the kind of aim of linking traditional variational Monte Carlo methods with recent progress in solving many-body problems. And also, later, there's an option for project 2 to link the Monte Carlo methods with recent advances in machine learning. So the notebook which you have here is then based on a simplified version of what we have in project number 1. So it's essentially going to deal with two particles interacting with each other. And this can be something like a electrostatic interaction. It could be any other type of interaction we could think of. And they are moving in a typical harmonic oscillator trap. So this is the kind of basic physics system which I'm going to look at. So the particles will have kinetic energy. They will be confined, the motion is confined by a harmonic oscillator potential, which mimics actually the kind of electric quadrupole fields which one can set up in the lab. And these kind of fields and these kind of trapping techniques, they have led to two very powerful ways of, for instance, measuring the masses of atomic nuclei. And there are two types of traps which ended up in Nobel Prizes in '89. They're called Penning traps and Paul traps. And essentially, these are electric quadrupole fields which are tuned so that you can trap specific ions in a small region in space. And then you can perform experiments on these particles. You can radiate them with a laser, or you can put them in a magnetic field and then test basic quantum mechanical properties of these systems. So the topics which we need to deal with today, after a repetition of what we did last week, is the Metropolis algorithm and how we're going to implement that. So for some of you, this will just be a repetition. But the basic Monte Carlo method deals with a multidimensional integral, which then defines the expectation value of the energy. And in our case, we don't have the exact wave function. R contains the different quantum mechanical degrees of freedom, and alpha represents a set of variational parameters. So for project number 1, the number of variational parameters is not going to be that big. And using the variational principle, we can actually show that this energy here is normally equal to or larger than the exact energy for this specific Hamiltonian which we have. And here we have defined, as we did last time, the positions to be this uppercase R to be the collective variable for all the individual single particles. So we actually do specify the positions of each single particle. In addition, we can have other quantum numbers like spin and other quantum numbers which may be needed to define the specific particles which we have. And then we have parameters. And these parameters alpha are the parameters which we use then to describe this trial wave function. And with the variational principle, we can actually show pretty easily that the energy we get when we don't have the exact wave function is always larger than the exact energy. Now, one of the things which we did last time was to convert this integral which we had in something which looks like a statistical expectation value. And the standard way to do that is then to define a quantum mechanical probability as we did last time. And then we would rewrite the expectation value in terms of a new quantity, which we call the local energy. And this is actually the quantity where we are going to spend a lot of CPU cycles in evaluating, because this quantity here is going to include the second derivative, which comes from the kinetic energy. And that's the second derivative acting on the trial wave function. And this is something which lends itself nicely for automatic differentiation, as we are going to come back to a little bit later. Based on this, we could then define the expectation value in terms of this integral, which now looks like a statistical expectation value. So we would have a probability distribution times the quantity here. And we're actually calculating the expectation value of the local energy, as it's called. And when we run a Monte Carlo calculation, when we use the law of large numbers, what we are hoping for is that this n, which is the number of Monte Carlo cycles, becomes large. Then we're actually approaching the true value of this integral. So typically, we are going to run the sampling over these different positions for millions of times. And hopefully then we are going to get a result which is going to be pretty close to the exact value. So a very simple Monte Carlo calculation, which implements this. We start with the initializations, fix the number of Monte Carlo steps. We would choose an initial position and variational parameters and calculate the trial wave function at an initial position. And then we initialize the energy and the variance and start the Monte Carlo calculations. We calculate a trial position where we have a step variable, which is defined by this quantity step here. And this is a quantity which we would tune. So this is normally called the simple or the brute force Metropolis algorithm. And then we implement the Metropolis algorithm. And if the step is accepted, we update the position, and then we update the averages, and then we finish and compute final averages. This is in essence the Monte Carlo framework, or what you might call the Monte Carlo algorithm. Then the Monte Carlo algorithm has a new algorithm for choosing whether you accept or reject the suggested move. And that is the Metropolis algorithm. And last week we discussed some simpler cases where we had a simple trial function, etc., etc. And the only thing I wanted to bring up is actually the harmonic oscillator, which to a very large extent mimics what we are having in the first project here. So we would start with a harmonic oscillator in one dimension. We put h bar equal to 1, the mass of the particle equal to 1, and the speed of light equal to 1, all the kind of physical constants that are set to 1. This is normally called setting things to the natural constants. And we have a oscillator frequency which we also put to 1. And in this specific case, what we have is a trial function, and the exact solution to Schrödinger's equation for the lowest lying state is given by alpha equal to 1. We can calculate the local energy. We can then calculate the integral and obtain the expectation value of the energy. So we have analytical expressions in terms of these parameters alpha. And we can similarly calculate the variance, which is given by the energy squared minus the expectation value of the energy squared. So, and then what we had was a simple Python program here, where we set up the trial wave function. We set up the local energies. We have simple analytical expressions here. And when we run through the code, we have 100,000 Monte Carlo cycles. We put the step size to 1. And then we initialize old positions and new positions. So these are going to be matrices actually, if we are dealing with this in more than one dimension. If not, this is just going to be a vector. And then we run over the variational parameters. And in this case, we know that the minimum is at alpha equal to 1. So we simply calculate the expectation value of the energy around a specific number of these alpha parameters. And now we run through the number of Monte Carlo samples. We produce a new position. We produce a new wave function. And then we have the metropolis test, which is the ratio between two probabilities. And that's also why we get rid of the normalization constants. If we go back a little bit and we look at the results here, and the definitions, you see now that the probability itself is probability density function or just probability distribution. So I will sometimes call it probability density function or probability distribution or just probability density function. Or I will just call it a PDF. So one of the things which is a little bit, how to say, less welcome to calculate is actually the denominator here, because that is a multidimensional integral. So if you have 10 particles in 3 dimensions, this is a 30-dimensional integral. Now, this means that when we now set this up, we have, in the metropolis algorithm, we have a ratio between probabilities. And the old position is now given by the new position if the move is accepted. We update the old wave function with a new one. We calculate the local energy, calculate its contribution to the expectation value of the energy, which would be added even if we didn't accept the move. And then we calculate the energy squared. And then we have the energy, we divide by the number of cycles. And then finally, we have the variance, which is the expectation value of the energy squared minus the expectation value of the energy itself squared. And then the error is the square root of the variance. We haven't subtracted a -1 here, even if there is a bias due to the fact that we don't know the exact energy. So the mean value which we calculate is an approximation. But we are leaving this out because the number of cycles is going to be so large that we will barely notice this -1 factor. And then we calculate the energies. And what we saw then is that we have a pretty good reproduction. So the blue dots here are the Monte Carlo simulations. The red line is the exact result. And we can actually get a smaller error here if we actually increase the number of Monte Carlo cycles, because when we are away from the equilibrium or the most likely position here, the most likely value for the variational parameter, then we will have the larger fluctuations. And you can see that same with the variance here. And the variance, when we have the exact wave function, is exactly equal to 0 when we have the exact wave function, which gives now in these specific units we've chosen, it's actually dimensionless energies. It's a 0.5, and it has an exact value when alpha is equal to 1. And you can see that from the program. So this program can actually serve as a kind of skeleton for your first program when you're setting up the Monte Carlo calculations. And you're going actually to run these calculations with 1 and 2 and more particles. And without any interaction, this gives us a very useful test, because then we know the exact answer for a system of many interacting or many non-interacting particles. But the topic which is interesting for us now, and I'm going to use the slides here, is the metropolis algorithm itself. And the metropolis algorithm is one of these really, really famous algorithms, and you will encounter it everywhere. If you go into computational finance, you're going to encounter the metropolis algorithm. If you're looking at the diffusion of a contrast liquid, if you're trying to figure out where a tumor is located, and you would inject a contrast liquid in a patient and just see from the scans then where the tumor could be localized, you can simulate this with a Monte Carlo simulation. But with the metropolis algorithm. But before we do that, let's now take a quick look at what we need to include in our program. So when we are going to develop a program now, there are several elements now which are going to be important. So what we are going to have here is building a program, build a VMC program. And there are several elements which we need to look at. So clearly we need to identify the system which we have. And then we need to define what kind of solver we want to implement here. And in our case, the solver is going to be a Markov chain Monte Carlo. So we are going to put a header for this. And this is how to build a code, a VMC code. So in our case, the solver is going to be what we normally call a Monte Carlo Markov chain, or Markov chain Monte Carlo. And this is normally written as MC squared. And when we build up such a Monte Carlo Markov chain code, one of the things which we need then is to find the sampling rule. So how we accept a suggested move. This is normally called a sampling rule. And in our case, the sampling rule is going to be given by the Metropolis algorithm. So one, we can have the Metropolis algorithm. We also have something which is called Gibbs sampling, which if we have time, we may say something about it. And these are some of the most common types of samplings which we can have in Monte Carlo calculations. Then, when we have, if we are still looking at this solver part, what we need as a next piece, and this is very important, is to be able to evaluate the errors. And this leads to resampling methods, which are normally called, and you probably have met some of them already. One of them is the bootstrap, which normally is applied to data sets with fewer samples. We have something which is called a jackknife, which is also a method which has been used to resample and get a better evaluation of the errors. We have something which is called blocking, which is the method of choice when we are dealing with millions and millions of data. So the Monte Carlo calculation is actually a calculation which, when we have evaluated these integrals stochastically, we need them to perform an evaluation of the standard deviation. And we want to be sure that the standard deviation we are evaluating has the correct values. And this can normally be done with resampling techniques, which allow us to give a better estimate of the standard deviation, which is the way we evaluate the errors. Then we also have an optimization part. And this optimization part is normally given by methods like a gradient descent. And many of you have encountered methods like standard gradient descent. You have met stochastic gradient descent with and without momentum, stochastic, GD, and etc., etc. And what we find in this part is a part which is now going to give us the optimal parameters. So that gives alpha optimal, which we normally denote with a hat on top of it, which is given by alpha hat. And that is going to be given by a collection of all these alpha values. So these are the parameters which give the best description of the total energy. And we would have m-1 of these parameters here. So we are going to implement things which many of you have seen before, and these are typically gradient methods. We're also going to look at other topics. which are meant to improve the convergence of Monte Carlo calculations. And one of these is a method which is called a backflow, which we are going to describe a little bit later. There are other methods which are called stochastic reconfigurations and so on, which are normally methods which help in speeding up the convergence of a Monte Carlo calculation. Then we are going to have high performance computing topics. So high performance computing topics, which is normally shortened to HPC, high performance computing. And in our case, we are going to look essentially at the MPI, which is called message passing interface, which is one way to set up a parallel calculation, which is normally tailored both to distributed and shared memory architectures. And then we also have something which is called Open MPI. And for those of you who follow IN 4200, you will recognize many of these methods. Then we have other types of solvers, elements of the solvers. Instead of using, let's say, a traditional variational Monte Carlo with a trial wave function, we can actually use other types of many-body methods. So we have diffusion Monte Carlo, and we are going to mention some of these techniques a little bit later, but we will not implement them. And then we have other many-body methods. So these are ways to solve the quantum mechanical many-body problem. Now, the next thing which we haven't mentioned is actually the system itself. And here we have elements which we also need to think of. So if we go back again, so what you see on the right here, these are the kind of algorithmic technicalities which we are going to cover here. Then, if we go back to the system part, that clearly is something which then defines the trial wave function. So whether these are fermions or bosons, we need to define, so this is one important element, and then we obviously need to define the Hamiltonian of the system. So what kind of motion the particle is subject to, if there is an external potential which confines the motion of the particle, if there is a strong or weak interaction, etc., etc. So when we look at the Hamiltonian, what we need to calculate here is the local energy. That's an important quantity. And we need to take the derivative, the second derivative of this trial wave function, which we put up here. So this is a trial wave function, and this trial wave function defines a probability. So we need to set up the derivatives, we need to calculate the local energy, and we need to find the expectation value of this local energy. And in the way we are going to identify the expectation value is either by the standard statistics representation, or we may actually use the standard Dirac bracket notation for an expectation value. So essentially what we do now is to calculate the expectation value of this local energy, where this quantity is now given by an integral, where every point here, R, the vector is an element in a domain. We have a multidimensional integral. We have a probability distribution, which depends on R and the variational parameters, and then multiplied with this local energy, which depends on R and these variational parameters. And this is the quantity which we typically want to estimate. So the other thing which we can do, instead of having a trial function, which is based on lots of physics assumptions, we could now replace, and this is a potential path for project number 2. So replace psi of t with a neural network. And as I mentioned last time, for those of you who follow Physics 5429, there is a possible overlap between one of the projects there and the project which we are dealing with here. But what you see here now defines essentially the kind of topics which we are going to cover in this course here. And there will be technicalities around the setup of a Monte Carlo calculation, like this backflow method, the calculations of gradients in the most efficient way, etc., etc. And obviously, one of the techniques which comes in is also automatic differentiation. So what we're going to do now is actually to start looking at one of these very, very important algorithms. I should also add here that we have, when we look at the Metropolis algorithm, which is a central algorithm here, we have something which is called importance sampling. And that's going to give a better way to perform the Metropolis sampling. And this is something which we're going to cover pretty soon. We will actually discuss that next week. So this sets up the basics of a variational Monte Carlo calculation. And when we have implemented all these elements, then what we will have is something which is as close as possible to a professional code, which you could actually use to do research with. In particular, if you're interested in solving many-body problems using stochastic methods. But let's go back to the slides, and we are going to take a look now at the derivation of the Metropolis algorithm. And I'm going to do that using the slides here. So the algorithm itself is an algorithm which is extremely simple, and that's why it's so popular. It's based on two essential principles. So one is called the ergodic principle, which basically means that if you were allowed to simulate for an infinitely long time, you should be able to sample all the possible positions which a system can have. In principle, we will not be able to that, but if the algorithm is not ergodic, it means that it will have a bias in the sense that you may have a path in your space which will be preferred. And that is not wanted, because that means that it will give a bias in the evaluation of a multidimensional integral. So what we have is a method to sample a normalized probability distribution by a stochastic process. So we define this P of I to be the probability of finding the system in a state I after a given number of steps n. And then the algorithm is sample a possible new state with some kind of probability. And then you accept a new state with a probability AI to J. So this is normally something we would call the acceptance probability. And then we use this as an example. With a probability 1 minus this AIJ, the acceptance, the move is rejected because I have only two possibilities. So this is a binary system. I reject the move or I accept the move. So I am having a probability for making the transition, and then I have a probability for accepting the move. And clearly not accepting the move must be 1 minus not accepting the move. The important thing here to realize is that in principle, we have no idea of what this probability is like. If we had known the probability, most likely we would not have been here preaching about variational Monte Carlo methods, because then knowing the probability means that we know how to sample the system. So the probability distribution is in principle a multidimensional object. So even having the probability distribution may not have led us to something which we could do within reasonable computational amounts of time. But what we can do now is to model this probability as the product of a probability of making the transition multiplied with the probability of accepting that specific transition. And then we are going to use the theory of Markov chains, which simply says that the properties of this T and A, they are such that when the number of iterations or the number of moves goes to infinity, then this probability becomes independent of time. And so that what we have reached then is the final equilibrium position for the system. So if we then look at the dynamics of this, it can normally be written in terms of a equation here, which is actually the standard equation for Markov chains. So we have a probability here, where we now multiply with the probability of accepting or making the move, accepting it. And then we have the product of this probability here, which is given by the product of the probability of making the transition and, in this case, rejecting the transition. And since the transition of the probability of making some transition has to be equal to 1, so these probabilities obviously normalize to 1, when we look at the second term here, we can sum that up and we can single out this specific term here. So this specific term then is something which we can isolate, and we are left with the term here, where we have the probability, which I just replaced with a pi here when we take the limit n goes to infinity, because then in the limit n goes to infinity, this term equals this term. And then I get something which is called a balance requirement. And this balance requirement simply states now that these probabilities, the sum of making a transition from a state j to I, accepting the move, minus being in a state I and jumping back to j, and then accepting it, is equal to 0. So this balance requirement, and you can show that mathematically, and this becomes the second item in addition to the entropic principle. I'm sorry, not the entropic principle, the ergodic principle. We can require, and you can show that mathematically, that in order for this to not be stuck in what we normally call cyclic solutions, that means that the solution will repeat itself after some time, we reach a final equilibrium state or steady state. In order to achieve that, we enforce something which is called detail balance. And in this case, we can now isolate the individual contributions and we get this specific term here. Now, the metropolis choice is actually to maximize this value of A, so that what you get then is that you take the minimum of 1, and then you have this Pi, Pj multiplied with these quantities here, these transition probabilities, which is a quantity which we normally can compute, or we have an algorithm for it. If we assume that the process is totally reversible, what we could do then is simply to assume that Tij is the same as Tji, and then we would simply have the ratios between the probabilities. And that means that the acceptance probability is now given by this equation here. So we are going to take a small break, and then we're coming back to these aspects, and we're going to discuss a little bit more in detail what this actually means. So let's take a small break and then come back in some few moments.